Spectra Summit Series. Thank you so much for attending the Quantum Summit, and in this session you will hear from Pouya Dianat, the Chief Revenue Officer at Quantum Computing Inc. Pouya earned his doctorate in electrical engineering and joins us with over 18 years of experience throughout the photonics industry. Today he'll discuss TFLN devices for photonic communications and quantum computing. If you have any questions or comments, you can type them right into the Summit chat box that is on your screen, and if you missed part of today's session, you can always come back later and watch it on demand. That's all from me. Pouya, we appreciate you for taking the time to join us here at Photonics Spectra's Quantum Summit.
Thank you so much, and for having me here. I'm very happy to be part of this, and I hope that the audience enjoys the presentation that I've prepared. Here we go. Okay, so thank you, everyone. My name is Pouya Dianat. I'm the Chief Revenue Officer at QCI, and today I'm going to talk about what we do at Quantum Computing Inc. And how it relates to the Lithium Niobate and what are our efforts in that. Before I start my talk, I would like to, if you don't mind taking a couple of minutes, moments reading through the forward-looking statements in here and the disclaimers associated with that. Now, with that, let's jump right into it. So first and foremost, here at Quantum Computing Inc., as the name suggests, we focus on the quantum technology and we leverage the nonlinear quantum optics to enable innovative solutions in computing, datacom, machine learning, and beyond. We are headquartered in Hoboken, New Jersey, where our hardware team and the R&D team and the test team sits. And we have offices in Arlington, Virginia, and we have our thin film lithium niobate dedicated foundry based in Tempe, Arizona. And that's where we do the peak manufacturing, packaging, and assembly. Now, I would like to first focus on how a quantum computing company needs a thin film lithium niobate. The heart of our technology is basically the architecture that you see on the right side of the screen. This shows what goes into our quantum computing and it's a sort of processing that we do on photons to be able to implement operations and to be able to perform math through our photonic quantum computing system. As you can see on the architecture, there are many elements, an n by n Mach-Zehnder mesh. That's where the encoding of the data happens to the photons. There is loss medium, there is optical amplifiers and fiber loop, and lots of all optical elements that you see here. And all of these need to be very high performing optical devices, and that is where we actually leverage the unique features of thin film lithium niobate. So for us to be able to build our quantum computing computers, we need to use this material system, thin film lithium niobate, and that's been the motivation behind having this material in our within our stack. What differentiates Quantum Computing Inc.'s technology compared to other technologies that are out there is that our technology is commercial, scalable, and available. So we have quantum that works today. And as you can see here, there are three elements that is very important to our technology. One, we leverage nonlinear photonics, and that gives us more degrees of freedom and flexibility in processing and manipulating rays of light and photons. The other thing that's unique to us is our qubits are in the defined time domain as opposed to the spatial domain or the physical domain, and that gives us the scalability aspect to our quantum technology, because then we can fit more qubits in a given fiber loop, and therefore we can increase the number of qubits that we have. And all of this are enabled with a material system called thin film lithium niobate, and we build photonic integrated circuit based on thin film lithium niobate that will eventually go into our quantum computing as well as other verticals of our quantum technologies. So with that, there are three aspects or three verticals or three core technologies that we work on. We capture, compute, and communicate data. Um, and all of these is enabled by quantum photonics and quantum photonics as the core technology. When I talk about capturing of the data, I'm talking about basically quantum sensing feature that we have on the single photon regime. That operation can have quantum aspects to it. Then we do processing of the data through our compute platform. And once that is done, we can also always communicate the data through our quantum communication scheme that we have. So what is different about QCI is that we are fully vertically integrated, uh, and that means that it enables us to offer different products at different levels. At the very bottom of this pyramid, we can offer services like thin film lithium niobate foundry service, R&D, and non-recurring engineering services. We can offer the chips that we make in our foundry as standalone products like package modulators or periodically pulled lithium niobate structures. We can offer modules like quantum random number generators and SPDC sources and alike. These are the modules that we need to build to go into our machines, and those are also available for general market to use. We can offer subsystem level products as well as, for instance, Dirac vibrometer or our quantum communication systems. And we can also go on the very top of the pyramid and mix and match different solutions that we have to offer system level solutions as a turnkey solution provider based on the technologies that we've got. So there is a versatility in the kind of products that we offer to the market, and whoever is interested can get access to those. The core part of the way that we do things is that we are approaching it in a modular way. There are parts that we do in-house: linear optics, nonlinear optics, electro-optics, and photon sources are the parts that we build in-house. And there are parts that we leverage the existing ecosystem, like FPGAs, chip packaging, laser sources, photodetectors, photodiodes, etc. But these are all different building blocks, like Lego pieces that we can put together in different formats to come up with different technology lines and therefore different product lines. So if we go and do a little bit of mix and matching of these core parts, we'd come up with 4 areas of focus. Our first and foremost is our quantum processing unit, or QPU. That's a core or the heart of our quantum computing architecture, and that is very good for solving NP-hard problems, for optimization, simulation, and differential equation solving. It's a gate-based quantum open system, and it offers speed, capacity, and energy efficiency in computing. If we rearrange the blocks and look at them differently, we have a photonic intelligent unit, or PIU. It is effectively AI on the edge, and it can help with optical signal processing and offer speed, capacity, and energy efficiency in artificial intelligence. Now, we can, again, if we rearrange this stuff, we would go to our quantum intelligence sensing offering or technology, and that's where we can combine quantum sensing and data processing all in as part of the hardware and not as separate entities. And basically, we will have single photon lidars, vibrometers, quantum enhanced spectroscopy, entanglement, enhanced and noise resilient sensing. And it offers energy efficiency, precision, and robustness. And finally, again, by rearranging these building blocks that I mentioned, we have our quantum cyber module that is good for quantum authentication, encryption, and quantum physically unclonable function chips, and quantum random number generation. Now, this part is actually very unique to QCI and the way that we do things, because we can have the authentication channel in a communication in a quantum communication system also to be quantum. The majority of or as far as I know, any communication channel right now that we have has an authentication channel which is classical, which means that if there is an intruder to that classical channel, then to that authentication channel, then that can compromise the the whole communication. But if you also make that authentication channel into quantum, that would give you a more secure way of transferring information from point A to point B, and that can come with added security and added privacy for whoever the user is. Now, the quantum systems that we have, the quantum computing system that we have is something that actually performs today. It's not the technology of tomorrow. It's actually has functionality and utility today. And we particularly showed that by benchmarking it against a well-known algorithm that exists in the machine learning field called XGBoost or extreme gradient boosting. And what this algorithm does is that it actually, based on a series of weak classifiers, it combines them to be able to have a strong classifier. And what it means is that assume that you have a data set for fraud detection, for instance, of a data set that you have from your financial institution, or a financial institution has a data set that based on some different weak classifiers within that data set, you can combine those to be able to detect fraud. So you combine those and you train your AI machine based on that to be able to detect any upcoming data that may be fraud. That is typically done with GPUs and CPUs. So you do the training and then you come up with the weight updates and add tree to ensemble and then go through this loop. And finally, you get the weights and assemble strong classifiers. And there is data sets out there that you can have access to and try it out classically. Now we have come up with we have developed this algorithm in-house called CVQ-Boost, which is continuous variable quantum-inspired boosting. And through that process, we've been able to implement similar training with our Dirac machine, which is our current quantum computing platform that we have. And what it does is, if you look at the equations that are on the screen in here, the Hamiltonian of the system, which is on the right side, the equation that you see, has a very strong resemblance to the equation that you see on the left for training the AI. So with that, it means that we can map the actual math problem for training into the Hamiltonian of the system and be able to go through similar training. And this is, we've developed the algorithm in-house, and it's called CVQ-Boost, and that's something that we have benchmarked. And what is important about this is that it makes for an explainable AI feature by using our technology. Because in the conventional way of doing training in AI, what happens in the physics of it is unclear. We just feed the data and then get the updated weights, and we don't know what happens in between. But in our case, given that the physics and the equations and the Hamiltonian of the system is very well known, we have a situation that we can actually explain what is going on throughout the training and why we get the weights and how we can assemble this strong classifier. And that is very important for many reasons. For instance, for fraud detection, you want to be able to explain why you are assigning a new data as fraud. And with the conventional AI way, there is not a clear path to it, but with our method, you have an explainable way. And we have actually benchmarked this, and the demo of this is available here that I'm showing it here. Here you can see what the benchmarking that is happening between the classical and the quantum way that we are doing it. And as you can see on the screen, the quantum approach can accomplish the training much faster than the classical approach. And you see just right at this moment, the quantum approach finished the training while the classical approach is still ongoing. Now, mind you that I did the capture screen of this one, so this is a recording of what was happening, and I did it at 4x faster. But the size of the data set that we have in here has 800,000 records. So that is a very large data set. And the reason that it's important is that the larger the data set that you have, it means that your training is going to be more accurate. So ideally, you'd like to have a larger data set. But in conventional ways, that comes with the trade-off that the larger the data set, the longer the training time, therefore you lose the real-time aspect of it. But if you use our quantum computing solution, quantum computing computers, you can process very large data sets, 800,000 records in this case, at a fraction of the time. And that gives you the capability of being able to update your training as the time passes. And that is important for applications such as fraud detection in financial transactions and so on and so forth. Now, having shown all the data that has showed so far, there we have to come up with a way of physically making this system. And our approach is based on photonics, and it's enabled by unique features that we can harvest from the material of choice. And there has been some thought process that have gone into what is the best material for that. And there are certain criteria that we needed to meet. We needed wide transparency window for the material system that we were going to use. As you can see in here, it's going from UV to visible, O band and C band. We had some device requirements that we needed to meet. Importantly, high second and third order nonlinearities from the material, and high refractive index, ideally larger than 2.1, to be able to get light confinement features. And we needed to have some manufacturing requirements because we not only want best performance, but we want to make something that can be manufactured and can be manufactured at scale. So, and here are some of the criteria for the manufacturing that we needed to think about and incorporate into the way that we thought about our computing and quantum platforms. And there has been a few different candidates, particularly lithium niobate as the first priority, lithium tantalate as a second, and barium titanate as a third. But from all of these materials that I've named in here, it seemed that thin film lithium niobate is the one that actually fits the best for our computing modality and for our quantum technology. The main reason is it's the most material with a robust supply chain. So with the thin film lithium niobate, you get many years of research and actually the products deployed in the bulk lithium niobate format, and there is lots of knowledge that could be leveraged for delivering on the thin film format as well. So among all these materials that I mentioned, thin film lithium niobate was the material of choice. With that, we can get fast switching speeds above 100 gigahertz, low VPI values, less than 1 volt, wide bandwidth, CMOS compatibility, being able to do phase modulation, and strong confinement for light, and large nonlinear coefficients chi2 and chi3, and very low loss material and large electro-optical effects. So having said all of that, this table in here basically summarizes what I just said in a nutshell in this table. And with the electro-optic modulations, we can get modulators that are very much in demand for in datacom nowadays for the need for 3.2 terabit per second data rates that people are looking at. With the chi2 nonlinearity, we can get into periodically pull lithium niobate waveguides and micro rings, and get all of those different features that you see on the bottom of the screen. Similar idea with the chi3 nonlinearity. Now, this is where we are today in 2025. We have our quantum computing machine that is a benchtop system operating at room temperature. And for us to be able to get it into miniaturize it and make it get very small to get into photonic quantum computers that can be made into chips, we needed to have our own dedicated fab for processing the thin film lithium niobate. The reason that we decided to own our own fab and build it from scratch in Tempe, Arizona, was that the company had reached a level that sourcing the thin film lithium niobate and processing it at user facilities or at universities was not providing high performance enough enough components in a repeatable and scalable fashion to be able to make an actual product out of it. So strategically, QCI decided to build this fab and own its operations dedicated to thin film lithium niobate, and to be able to go from the benchtop system that we have into the chip in the future. And along the way, it has so happened that there is interest in other market verticals for thin film lithium niobate, and we had the capability of serving those markets as well. So therefore, we have the QCI Foundry that can offer fab as a service for MPW runs, dedicated wafer runs. We can make electro-optic modulators, PPLNs, filters, and some other elements that are listed in here as well to the broader market, while we are also going from our vision today to our vision for tomorrow. But the basis, the knowledge for this fab was based on the prior work and prior work that we had done, that the team had done at user facilities and at universities. Given that the hardware part of the QCI is actually a spin-off of the work that was done at Stevens Institute of Technology. So I'm going to present here some of the prior work that's been done before we build the fab, and now we are actually transferring and stabilizing the processes in our own dedicated fab. So the first and one of the most popular elements is an electro-optic modulator. There has existed the bulk version of it, as you can see in the image in here, which between the electrodes there is around a 20 micron gap, and then there is a thick electrode layer of 10 micron. So what happens in that case is that the confinement of the field is spread over a wider area. So therefore you have less control over how you can manipulate the light that is going through it. But in the thin film version, you can reduce the spacing to 5 micron and reduce the electric thickness to as low as 2 micron or even lower. And that gives you better confinement and better control of the electric field inside the material in thin film lithium niobate, and that gives you better control over the modulation of light through the electro-optic effect. And the images on the right that you see are some of the EOMs that we've made and throughout the through our fab and for bringing our fab online. Previously, we had shown that we can make cascaded electro-optic modulators, as you can see in here, a cascaded EOM. And the reason that you do that, you go that route, basically you put two TIs in series, or in a cascade format, you can get an extinction ratio that is as high as 50 dB. And that's, you can see the data on the bottom right, the graph over there. That is important for us because that helps us to increase the number of qubits that we can attain in our quantum computing machine. So that is one of the key elements for us, but it also finds other applications in other verticals as well, for radio over fiber and applications such that. The electro-optic modulators that we have demonstrated, one key element of them is the V-pi value that you can get, and as you can see here in different publications, we have shown that we can get V-pis as low as 1.6 volts, and that's very good because you need a low V-pi to be able to drive the modulator with current DSP formats. It's very important for this voltage to be low because DSPs need to be operating at lower power, therefore saving a lot of power and energy for the overall system. So that's why the thin film lithium niobate is an important material, because of that aspect that of the low V-pi that we can get. Throughout bringing up our foundry, we recently actually have been making these electro-optic modulators in-house, and so far we have shown EOMs that are at 44 gigahertz, operating at 44 gigahertz, and have measured up to 60 gigahertz, and they can actually now we are working on designs and optimizing our processes for it to go higher and beyond. The goal is to go and reach more than 100 gigahertz, and we are currently working on that as well. Another feature special to thin film lithium niobate and materials basically with large Chi2 and Chi3 nonlinearity is having the periodically pulled lithium niobate structures. So in such with PPLNs, we can do phase matching in a way to be able to combine two photons in a nonlinear format that have frequencies of, let's say, omega 2 and omega 3. And then the output when the light propagates through this waveguide would be a photon with frequency omega 1, which equals omega 2 plus omega 3. So you can do up conversion and down conversion in such materials. And that's what you can see that theoretically depicted in here. There are simulations done. You need to confine light very well and do the very accurate phase matching for that. So PPLNs are other things among other components that we have demonstrated previously that we can do, and here are some more data into that of the conversion efficiencies, of the wavelength, and different aspects of it in a waveguide format. And we can also make PPLN in microring formats. We can, as you can see in here, the SEM images in the middle show a pulled device, and that's why you see the differences in color, because that showed differently on their SEM. We can make microrings and put actually thermally control them very accurately. On the bottom row, that's what you see on the microring format. With from 0 milliwatt to 40 milliwatts of power applied, thermal power applied, you can shift the resonance of the resonance wavelength of the microring and effectively build a filter from that. Another optical component that we have made that is popular is frequency combs. And that's an area that we have demonstrated. We are working on improving this in the future. So the data here is just a matter of proof of concept that it can be done, but there is room for improvement there's room for improvement on making this device with frequency combs even better. With the microrings that we have, we can make tunable filters. I mean, so this data I showed in the prior slide, but what is important in here is that on the image in the top middle, that gives you the capability of making an on-chip spectrometer, basically, because you can, just by applying the thermal power to the microring, be able to filter light, and basically you can decipher the light that goes through a system by applying different, tuning it and applying different filters and making it very accurately. So it can take a device that is bulky nowadays to very much a chip scale deployment of that. For tunable filters, the previous one that I showed you were at the wavelength of a little bit more than 1550, larger than that. So that's in the infrared or near infrared. But here we have shown it at a different resonant wavelength around 766 nanometers, and similar thing can get applied in here by applying the thermal power. We can tune this filter very well at a wavelength that is closer to the visible. And by the way, that's another feature of thin film lithium niobate, that it has a very wide wavelength, that bandwidth for the wavelength that it can that light can propagate through that. Going back to the PPLN's base structures, we do currently make periodically pulled lithium niobate based entanglement sources in-house. The bottom right image that you see is actually an actual product that we have available for sale that is based on bulk lithium niobate. So we do the PPLN, we do pull the bulk lithium niobate, and we are able to get entangled photon sources out of it with a very stable format, as you see, and with a very stable count rate that you can see in the graphs over there. So the plan is that box that you see on the bottom right, it's a little bit bulky, but it's not too big. You can hold it in one hand, but still, if the vision is to go toward chip scale deployment, we need to miniaturize that. And thin film lithium niobate is a material to do that. If we go to the thin film format, we can go from the bulk stage to the small scale, integrate laser, and be able to make it very very small. So now, all of these prior work that showed something that we can do at our foundry in Tempe. So I'd like to introduce the QCI's Foundry, the thin film lithium niobate foundry that we built for a purpose, but its services is available to the broader market. We can etch low loss waveguides. We have set a record of reaching roughnesses of sidewall roughnesses of less than of around 300 picometers. It is an important feature because with a roughness as low as 300 picometers, you minimize the light scattering through the waveguide, and through that you can reach waveguide losses that can be as small as 2 to 3 dB per meter. Now, this has been shown before. Now, the goal of the foundry is to reach this result in a repeatable and reliable format. So that's a challenge that we have taken on us to reach this sort of performance in a reliable and repeatable format, and we are working on it right now. So we can put everything together and make it into photonic integrated circuit with Bragg mirrors, MMIs, and all different formats that you see in a very small format. And we offer an MPW run with a flexible schedule, fast turnaround time, and we have our standard PDK design for 1550 nanometers that is available on GDS Factory right now. And if you are interested to get access to that, we can go with thin film lithium. You can send me an email to thinfilmlithiumniobate@quantumcomputinginc.com. And with that, I'd just like to summarize everything that we said in this slide, different capabilities that we have at QCI Foundry. And with that, I would be happy to take any questions. Thank you.
Thank you so much, Pouya, for introducing viewers to TFLN for Photonic Quantum Computing. To everyone that's joining us in the audience, if you haven't already, you can type your questions and comments into the Summit chat box, and do not worry, if you have not been answered yet, you will be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the Quantum Summit. Thank you all so much for joining us.